Okay, great. Let's continue. So last time we spoke a little bit about the moduli of Hodge structures, and if we talked about these period maps where we have a base S with, say, a smooth family of projective varieties over it, we get a map to this thing we called D mod GZ. And one of ours, D was some Grassmannian variety, and GZ was some arithmetic discrete group acting on it. And one of our goals, goal one, was to give this a definable structure such that these period maps here become definable RNX structure. So I want to start by saying a little bit of generalities about how one gives such a quotient to structure. And in some sense, one of the goals for today will be to reduce this statement about definability to a purely analytic statement about variations of Hodge structure. And we'll say something about that statement sort of later on, but I sort of want to get from the logic to the analysis. And maybe something I should say that I didn't emphasize enough last time was there's obviously been a lot of work in Hodge theory since its development in the mid-20th century. And what we're doing is basically in no way supplanting, like replacing any of that work. All of the analytic inputs to Hodge theory are still going to be ingredients in our theorems. It's just that o-minimality sort of gives a very nice language to summarize some of these results, from which you can then go on to prove other things more easily. So it's kind of a nicer foundational sum up in some ways. Okay, but let's first abstract from this and go to the following kind of general situation. So let X be a locally compact Hausdorff definable space. So it's some topological space with a definable structure for some o-minimal structure. It doesn't matter which one. And let's say we have gamma acting on X properly and discretely. Through definable automorphisms. So as a concrete example, you can think of this gamma acting on this X, which we'll apply this to. You can think of the integers acting on the complex numbers by translation, any number of results. But importantly, I want to point out that gamma is going to be a discrete group. So in no way does gamma have a definable structure. It's just that it's some group. And for each element of gamma, the corresponding automorphism of X is definable.
Can you remind us what properly means?
Sure. This word properly means that around every point, for every point P, there exists some open set U containing P, such that, let's even say, you can be more general, but let's say the set of gamma such that gamma U intersect U is not empty. Well, let's say this is finite. That's the general definition. So locally, there's nothing crazy going on. And you can even pass without much trouble to the case where this set is just the identity. That's sort of, yeah. Okay, let's say we have the following structure. Then our goal is to explain how to define a definable structure to the quotient X mod gamma. Okay. So one way of doing this, one sort of naive way, which ends up working, is you can actually pick a fundamental domain for the action of gamma on X. And if that fundamental domain is definable, you can just steal the definable structure from there on the quotient. It turns out to be a more convenient to work in slightly more generality, simply because it's very hard to find exact fundamental domains, and it ends up kind of being besides the point anyways. So we're going to work with a slightly more general definition, So we'll say a fundamental set for this situation is some subset f of x, which is definable in whatever structure we're working in, and satisfies the following two conditions. So first of all, definable, and I want f to be open as well, and to satisfy the following conditions. First of all, I want f to contain at least one representative for the action of for every orbit of gamma. So gamma times f should be all of x. Second of all, I'm not going to insist there's at least there's exactly one element from each orbit, but I want it to be finitely many, and I want this to happen in a uniform way. So what I'm going to say is the set of gamma such that gamma f intersect f, this is finite. Okay, so I want there to be globally only finitely many gammas sort of involved if I restrict to f. And then the statement, there is then a unique definable structure on the quotient such that the map from f to x mod gamma is definable. Okay. And so to give such a definable structure is just to find a fundamental set f like this. So why is this true? I'll give a sketch. So let R sub f inside f cross f be the equivalence relation restricted to f, be the gamma equivalence relation on f. Then what is R sub f? Well, R sub f is the union over all gammas of the set x gamma x intersect f cross f. So because of the property 2 here, we have that this is definable because it's only a finite union. Each individual term here is fine. So this is definable. And now x mod gamma is just f modded out by this equivalence relation R sub f. So now we're just going to show the definable set by definable equivalence relation has a unique definable structure, and this is a well-known thing. And so this is now true by definable quotients. Definable quotients exist. For those who want a reference, because we needed one, so we ended up finding one in Van den Dries's book. Almost the very last thing he proves is this result here. And I'm not going to give the proof because it's a little tedious and I mess it up. But the basic idea is, first of all, you find any definable set of representatives for this equivalence relation. And you do this, say, for every orbit equivalence class, just taking like the smallest representative according to some lexicographic ordering or something. That gives you some definable set. And that's going to be fine on sort of a maximal dimensional component. Then you have to sort of fix it up by induction on the smaller components. So the idea is to first find some definable set of representatives and then kind of fix it up. Okay. So the other thing I want to point out is if you have two different fundamental sets, they can define very different definable structures on the quotient. And in fact, it's pretty easy to say when they define the same one. So f and f prime define the same structure on X mod gamma if and only if the following condition holds, and you can write it in a few different ways. So the asymmetric way to write it is that F is inside the union of gamma F prime for some finite set of gammas. So you need finitely many copies of F prime to sort of cover F. It turns out this is symmetric, even though it's written asymmetrically. And the asymmetric way, sorry, the symmetric way to write this is the set of gamma such that F intersects gamma F prime is finite.
Isn't this always the case?
Isn't which part the case?
Isn't this condition always satisfied?
No, it's not. So great. I'm glad you asked that question. So let me just give one of my examples to demonstrate why it's not. Let's let X be C, gamma be Z, so that X mod gamma as a set is basically C star, the exponentiation. Then you could take F to be the usual F. And Peter's in his lectures touched on this quite a bit. So if you take it to be this set, then you get C star with its usual definable structure, at least if you're in Rnx. But you could also take, for example, this set, where you take any two parallel lines, and then you can very much see that any two triaglets will intersect.
I see. Okay.
Yeah, so this is a very non-trivial condition on things. And in fact, I don't know if we'll get to talk about this, but this kind of stuff shows up a lot in sort of mixed Hodge structures with some generalization of what we've been talking about. And in this case, how to say, not all of these structures are equal. This definable structure is really the best one. Why is it the best one? Because if you care about the holomorphic data, then this definable structure will actually have sections. We'll have holomorphic functions that are global. For example, the exponential function will then be definable on this quotient. If you take any other definable structure, it turns out there's not going to be any non-constant definable holomorphic functions. So they somehow are not all created equal, and it's not entirely trivial to figure out which one's the best. So it's a very interesting subject. And Peter and Sarchenko have worked at the Torre case quite thoroughly. Okay, other questions? Cool. So why is this true? Let me just give a sketch. Well, so one direction is kind of easy. If this relationship is true, then you're fine. And the reason for that is sort of the following diagram. So this is the, let's see, maybe a little more precise about this. So let's prove the forward direction. So for the forward direction, we have the following diagram. We have F maps via inclusion to the union of these gamma F prime. Sure. Speaking, check 1, 2, 3. We're good. Back in business. Okay. Should I repeat anything, or like was it just lost the moment you said?
Probably from there.
Cool. Just to let me just quickly reiterate. Not sure where we were. We're trying to put this equivalence. So in one direction, if you do have this condition, you can look at this diagram because these 3 maps are definable. You can sort of go boop, 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 and get that this identity map is definable. And now we're trying to show that if you get the same structure, this condition is satisfied. And the trick is to look at this fiber product. This fiber product is definable. And therefore, it has finitely many components. Let me just add the word analytic, well, whatever, finitely many components in whatever sense you want to work. However, the components here are actually stratified by gamma because this fiber product is contained obviously inside this fiber product. This is just topological now. This is not a definable set because the projection maps can't possibly be definable. And this is just the union over gamma of the sets X gamma X. So if there are finitely many components here, that means only finitely many of these sets can be involved. And that exactly means this condition here about the finitely many gammas. Any questions? Oh, the chat has some. Oh, that's just from the last stuff. Okay. Cool. All right. So the important thing to do, we see now, is to give an appropriate fundamental set. Just to specify a definable structure on a quotient D mod GZ. And from there, we have to prove things are definable. Okay, so let's do this in our case. So let's remember, we have a lattice L and a form Q on it, together with an integer n. And then D check is the sort of space of filtrations on L, which satisfies some isotropic conditions. And D, inside this D check, is the space of Fs such that the corresponding LPQs, which are the intersections of FP with FQ bar, satisfy positivity conditions. The positivity condition I to the P minus Q, Q VV bar is bigger than 0. V is an LPQ, but not 0. So it's some open subset inside D check. And again, the case to think of is elliptic curves, where this is the projective space and this is just upper half plane. Okay, and we had the group G, the algebraic group G, with the space of automorphisms of L together with Q. And one important thing to recognize is if we look on D check, then actually DC acts on D check. Because what is the action? The action is just take your element and act on your filtrations. That's going to preserve all your Q conditions because we're looking at automorphisms preserving the form Q. But it's not going to preserve these conditions in general. And the point is that if you act by a complex element, you're going to mess up these LPQs in very unpredictable ways. Because you're going to get a gamma here, or a G here, and the G bar here. And so the intersection could go haywire. The dimensions could change. So GC doesn't act on D check, but on D, but GR does act on D. Right? And the point is that these are real. And so the action of G actually descends to the LPQs. So this is analogous to how like SO2C acts on P1, but only SO2R acts on the upper half plane. Now, let me introduce, our goal is to introduce something called the Hodge metric, which is a simpler piece of data than the full Hodge structure, but is very good at detecting degenerations, which is exactly this issue of non-compactness that we were bringing up earlier. So let's say we have a Hodge structure like this. Given an LQ and the filtration on it, we can define a Cartier operator, C, which will be, it will be a real map on the lattice, so the map on the lattice tensor R. This is called the Cartier operator. And it basically takes this positivity condition and turns it into a positive definite form, into a Hermitian form. So the way it's defined is C applied to a vector is I to the p minus q times that vector if this vector is in the pq part here. Okay, and because of a direct sum decomposition, this gives you a map on all of L. So it's a very simple thing. Particularly its fourth power is always the identity. And then we can define a Hodge norm, H of V, to just be Q applied to CV and V bar, whenever V is an LC. And this gives you a Hermitian norm on our vector space. So why? Well, the only non-trivial thing to check is positivity. Everything else is completely formal linear algebra, because everything here is linear. And positivity is exactly just rewriting that condition over there, right? If we're in LPQ, then putting the I to the p minus q inside, we get that this is positive. And if we have a sum over different components in LPQs, well, they're all Q orthogonal, so it will just all come out of the sum. Okay? This is a positive Hermitian form. On LC. And it gives you a positive quadratic form on LR. On the real guy, it only takes real values. Okay, so this is some kind of form you can define. This is sometimes called the Hodge norm of V. This whole thing is called the Hodge metric or the Hodge norm. And it very much depends on the place where you are. So just to give an example for how this behaves, again, in our familiar case of the elliptic curves, let's let L be spanned by E1 and E2, n equals 1, and Q is the symplectic form, U of E1, E2 equals 1. And let's say we're at a point, we have a Hodge structure of filtration, where the E1 0 part is spanned by E1 plus tau E2. And the 0 1 part is spanned by E1 plus tau bar E2. So to understand how the Cartier operator acts, for example, on E2, we write E2 as a sum of elements in here. So this is E1 plus tau E2 minus E1 plus tau bar E2 divided by 2IY, where tau I'm going to take to be x plus IY. So if I apply the Cartier operator here, I just hit this by I, and I hit this by minus I to the power of p minus q. So this minus becomes a plus. And if I work out what this is, you get E1 over y minus x E2 over y. Sorry, there's some loose chalk here. Maybe it's making it complicated to read. This is 2IY. And similarly, you can compute CE1, and I'll just give you the answer. CE1 is minus tau norm squared E2 over y plus something times E1. Doesn't matter which coefficient's here. I'll write it down. So then the Hodge norm, if we compute it, well, H of E1 is again Q of CE1 against E1 bar, which is just E1. So the E2 components, all we care about. And so we get tau squared over y. H of E2, if you compute it, is just 1 over y. And it's a positive form, so we can actually take inner products. And if you compute H of E1, E2, you get minus x over y. So if you represent this matrix in sort of coordinates, we get 1 over y minus x over y, 0, norm tau squared over y. Okay. So notably, this probably isn't so surprising, but if you're in the usual fundamental domain, which will make sense for us in a slightly more canonical way in a minute, then this sort of behaves under control until you go to the cusp. And as you go to the cusp, one of these guys shrinks and one of these guys grows. This entry always remains reasonable. So somehow the lattice degenerates as you go higher and higher. And as was pointed out, degenerations are really all we care about. And somehow a Hodge metric really captures that behavior. You can tell how degenerate you are just by looking at this data. And that's a general phenomenon. So let me write it in the following way. We end up getting a map, which I'll call phi for the moment, from B mod GZ, which is the space of Hodge structures on our LQ, to what? Well, certainly you can get it to positive forms, quadratic forms on LR just by associating the Hodge metric. And now what happens if we act by an element of GZ? Well, we end up getting the same thing, but with the basis change given by our element of G. So this respects Q, it respects the Cartier operator. So once again, we get this mod GZ, but in fact, I'll map even lower. I'll map all the way down to mod automorphisms of L. And what is this space? This is just the space of abstract lattices. Lattice like 3 billion groups with a quadratic form on. That's all we're getting here. Okay, now this group is of course much bigger than this group is general. I mean, not that much bigger, but this group is like GON, and this group is either an orthogonal or a symplectic group. But this space is much smaller. So it turns out this space, quotient out by this group, sits nicely inside this space, quotient out by this group. So I'll make it more precise in a second. But let me now that we have this sort of map all spelled out, it turns out that if we give a good fundamental set over here, in this very non-Hodge theory space, a very classical space, the kind of thing Minkowski studied, we can actually just pull that back and get a fundamental set over here.
Is this phi injective or?
No, this phi is not injective, but it is.
Finite to one?
It's not finite to one either.
Oh.
Yeah, it's not finite to one either. I'll explain very quickly why it's not finite to one. So somehow, what does the Cartier operator do? It acts differently on the LPQs, but it doesn't really. It really only cares about this P minus Q. So if you had like a weight 3 thing, and you had like L30 and L12, the Cartier operator acts the same on both of them. So what we have, let me write this down here. We have this decomposition. Let me say the 3 case just for concreteness. We have this Hodge decomposition. And the Cartier operator really only cares about these 2 pieces, L30 plus L12 and L21 plus L03. It acts by I inverse, some negative I on this, and I on this space here. So as far as the Hodge norm is concerned, it doesn't really care once you have this vector space satisfied, what you put here and what you put here. So there's some unitary group of choices that's going on here. Once you get rid of that indeterminacy, then this map really is finite to one. So you can very precisely say the extent to which it's not finite to one. It's exactly this issue here. Yeah. And this is also part of the reason why, well, I guess there's many reasons, but like if n equals 1 and you only had L10 and L01, this would not come up. And so that's one of the many reasons why weight 1 is so much easier. It's just a billion varieties, you have all this extra structure. Okay, let me describe what our fundamental set on this space will be. So suppose E1 through EM is a basis for L, and C is some constant bigger than 0. And let's say B is a positive quadratic form, on L. We say that this basis, E1 through EM, is C reduced if the following holds. We have 2 conditions. The first is we want these to be roughly ordered. We want B of EI to be less than C times B of EJ if I is less than J. And the second, which is more important, is that these EIs are roughly orthogonal. So B of EI EJ is less than C B of EI for all IJ. This is what it means to be B reduced, to be C reduced, sorry. So it's relative to an ordered choice of basis. And again, no, this really does mean almost orthogonal, right? If they're actually orthogonal, this is true. But this is a much stronger condition than just saying something about the angle between them, right? Because if EJ is much, much, much bigger than EI, the fact that there's only an EI here is saying they really have to be very close to orthogonal. And in fact, if you look at the upper half plane as a space of lattices, and you try to work out what these conditions are, they'll exactly give you these sort of rectangles up here, which are the fundamental sets you usually work with. So these analytic conditions, this was studied by Minkowski and Ziegel, a bunch of other people. And it turns out these are sort of the right, quote unquote, sets to work with in many different contexts, including this one. So let's call the set of these like S sub C. We'll call these sort of Ziegel sets, and of course they're relative to your basis E1 through EM. So Ziegel showed that the S sub C's are fundamental sets in the sense we gave over there for C big enough. And then our work of Ziegel, as well as Borel and Harish-Chandra, show that quite generally, it's like in the context of semi-simple groups, and even a little beyond that, if you look at maps like this, then phi inverse of these S sub C's are also fundamental sets. This one for the group at L, and that one for the group GZ. Okay.
Little puzzle. I mean,
Yes.
if you take C big enough, is
Yes.
this condition, are these conditions 1 and 2 automatic, or what am I missing?
No, why are they automatic? What condition 2 in particular?
Is this a positive form? So
Yes.
VEI is positive.
Uh-huh.
So, and you have only finitely many I and J.
Oh, I mean, for big enough C, everything will eventually be in here. Is that what you mean?
Yeah.
Yeah. Statement is for a fixed C, the set S sub C is going to be a fundamental set.
Of course, you consider all possible B's.
All possible B is for a fixed C.
Okay.
Exactly.
Yeah,
Yes.
okay.
Sorry, I should have been clear.
Sorry, it's fine.
No worries.
Yeah, okay.
Other questions? Cool. Okay, so this is now a purely analytic condition on our Hodge norm, our fundamental sets. So let me give one more lemma. So suppose we have some definable space Y, and we have a map phi, let me call it psi, from Y to X mod gamma. And F is our fundamental set. Right? We want to understand when this map is definable for the definable structure here, given by our fundamental set here. Okay? So this is definable if and only if there exists a lift C tilde from Y to X, okay, which is definable and such that C tilde of Y lies inside finitely many translates of F. So S finite. So very similar to our previous lemma from before. Note we don't insist, there's no reason to insist on C tilde being continuous. So you're welcome to chop up Y into finitely many pieces, which we're going to do, and just lift them all up. Okay? And the proof is the same as before. So if you have this, then just descend, because the quotient map is definable. And to show that this is necessary, consider the fiber product of Y with F over this X mod gamma, and you exactly get this result. So it's very natural when specifying definable structures in this way to try and understand when you have such maps. And so now we're in, maybe let me just say this in words, and then we'll pick that up next time. So now we're in a pretty good shape, right? Because we have our algebraic variety, our base, which we want, and we have a period map here that we want to show is definable. We understand definable structure here in terms of fundamental sets. And so what do we have to do? We have to really, we see now the theorem is not really about algebraic varieties. We take our base, we're going to cut it up into sort of open sets and open disks and polydisks, right? If Y is compact, there's nothing to check, as you have showed before. But the issues what happens in new generations, where you have these sort of punctured disks and punctured polydisks, then we're going to want to find a sort of good set of vectors up here for our lattice and show that these conditions are satisfied. So we've translated our problem about showing these maps are definable to something purely on like analysis for Hodge structures for these generations of maps. Okay, I think I'll stop here for today. Thank you very much. Yes. Of course. Yes. They both act on D, correct?
So there you're considering just the quotient of D by G of D.
Yes. G of R actually acts transitively on D. We didn't show this, but yeah, but G of R acts transitively on D. It's not too hard to show because G of R is so big, it's some symplectic or orthogonal group. You're just going to show that acts transitively on like flags. So G of R is very big. Again, it's like SL2R acting on the upper half plane. Yes, that's right. It can be interesting if you go to like jet spaces or tangent spaces, some kind of covering above D to model by all of G of R. But if you actually want to look at D, it's the model space of Hodge structures, you have to model by something much smaller to get something interesting.
Once you have your fundamental domain, now you can look at the period map
as something analytic other than our domain. Well, it's more like once we have our fundamental domain, we can now rephrase the question of definability in terms of analysis. Yeah. Other questions? Cool. So let's resume on Wednesday. Thanks.